Welcome to all. In the continuation of our discussion on organic spectroscopy, in the last video lecture, I have discussed on the mass spectrum, the part 1, that is a basic instrumentation and various process involved in the mass spectrometer, and what is mean by mass spectrum. In the mass spectrum, how you can identify the molecular ion peak and the base peak, and how what is the characteristics features of the molecular ion, and finally we have seen the how the metastable peaks are formed, and how it can be identified, and calculated theoretically. In today's lecture, it's a mass spectrometer part 2. As usual, we will see the outcome of this lecture. Today we will see the isotope peaks. What it will impact on the molecular mass spectrum, the nitrogen rule, and the determination of a molecular formula by using the molecular weight that is obtained from the mass spectrum. And finally, the mass spectrum of some of the selected compounds. So you cannot go for all the compounds, analysis of mass spectrum of all the compounds. It is impossible. Just I will highlight the representative compounds, and you can just extend your idea to the other compound also. And the important the rearrangement in as far as mass spectrum is concerned is a McLafferty rearrangement, and finally the Diels-Alder reaction. Let us go into the lecture. The first one is the isotope peaks. That means the molecular ion in the spectrum that is appears in the higher range, the highest molecular weight region. Okay, that is designated as M. And we depending upon the abundance of the isotopes of a particular atom, we will get M+1, M+2 peak, etc. Okay, so for carbon, we have the C12 and the C13. The C12 is a normal isotope, and the isotope which has almost 98.9%, and the C13 is the abundance of C13 is 1.1%. So that will show the M and the M+1 peak. The M+1 peak intensity is very, very low. One cannot easily identify it. But the isotope peak of chlorine and bromine, that's a halogens. That discussion is very interesting. So if you take the abundance, natural abundance of chlorine and the bromine. So the chlorine, we have the chlorine 35, that's abundance is 75.77%, and the chlorine 37, its abundance is about 27.23%. So almost 75 is to 25 in terms of percentage. And if we take the bromine, the 79 bromine isotope, the natural abundance is for 50.69, and 81 bromine is 48.31%. So almost 50 is to 50, almost equal proportions. So if we let us take the bromine, the molecule which contains a bromine. So the bromine, as already I have told, it contains two isotopes, the bromine 79 and bromine 81 of equal abundance, the 50 and 50 percentage, and 50% of the 79 and 50% of 81. Okay, so in the mass spectrum, if bromine is present in the molecule, we will get a equal intensity of m plus m and m plus 2. Okay, m plus 2. Okay, equal intensity of m and m plus 2. Okay, so let us take one molecule, that is a bromopropane. Bromopropane, the molecular ion peak, okay, it is its value of MBZ is 122, and the m plus 2 peak, the MBZ value is 124. Let us see the relative abundance. It is of equal intensity, that is a 1:1 ratio. So if the mass spectrum having a m peak and m plus 2 peak of equal intensity, one can just have the idea that molecule contains the bromine atom. Molecule contains bromine atom. Okay, and similarly, the chlorine has two isotopes, as already I have told. The chlorine 35 and the 37, the ratio in the percentage of 75 is to 25. So the chlorine, the spectrum of chlorine containing molecules are a pair of peaks of intensity 3:1. So we have the M. I have taken the isopropyl chlorine. There's a 2-chloro propane. So the M plus peak, which occurs at M plus M by Z value of 78, it has intensity of 70%. And the M plus 2 peak, it has intensity of 25% compared to this one. This is 75 and this is a 25. So 3:1 ratio. So if the mass spectrum contains the M plus and the M plus 2 peak of the ratio 3:1, one can just have the idea that a molecule may contain the chlorine atom. Let us go into the nitrogen rule. So see, all the concepts that is useful to confirm the corroborate the given the geometry or is given structure of a molecule. So whatever the ideas, the nitrogen isotopes, the metastable peaks, these ideas are combined to confirm the molecule. Okay, here the nitrogen rule, it is identify the nature of the molecular ions. Okay, so it states that a molecule with even number of molecular weight must contain either no nitrogen atom. Suppose the molecular weight is 128 or 104 or 150. These are even numbers. If the molecular weight is the even number, then the molecule will not contain no nitrogen, or if it contains nitrogen atoms, it must have even number of nitrogen atoms, that is 2 or 4, etc. If the second one is a molecule with odd number of molecular weight must contain the odd number of nitrogen. If the molecular weight is 123 or 141 or 175, so these are all the odd number molecular weight. If the molecular weight is this number, then one can say the molecule contains the odd number of the nitrogen atoms. The corollary means the main statement is there. From the main statement we are coming to some extra conclusion. That is a corollary. That is the even numbered molecular ion. If the molecular ion is even number, then it forms a fragments that is a daughter ions of odd number. Okay, so and also if the odd number, if the molecular ion is odd numbered, it forms the daughter ions or fragments of even number. So once again I can repeat, even numbered molecular ion forms odd number fragments, and odd number molecular ion formed even number fragments. So let us see the example. Here we have the nitrobenzene. The nitrobenzene forms a molecular ion. Its M/Z value is 123. It is an odd number. And as already I told, as already we have stated, so it must form the fragments of even number. It forms a fragment of nitronium ion. It has an M/Z value of 46, and nitronium ion and nitrosonium ion. It has a M/Z value of 30. They are even numbers. They are even numbers. So these even number fragments formed from the molecular ion, which is odd number, which is 123. And the second corollary, the even numbered molecular ion gives odd number fragments. If we take the phenol, the 2,4-dinitrophenol. 2,4-dinitrophenol, it forms a molecular ion of the even number 184. 184. As per the corollary, it must form the odd number fragment. It forms a fragment of M/Z 183 by the removal of one hydrogen atom. By the removal of one hydrogen atom. Or you follow my point? Okay. And the next concept is the determination of molecular formula of a compound from its molecular weight. Okay, so when the molecular weight can be obtained from the mass spectrum, and once we can obtain the mass spectrum, the molecular weight from the mass spectrum, one can derive the molecular formula by many steps, by using the many steps. So we can have the molecular weight, and we can have the reference compounds, and we can match the molecular with the reference compounds and find out the molecular formula. That is the first way. And the second way is the rule of 13. The rule of 13. In finding out the molecular formula from the molecular weight, by using the rule of 13, we must form a base formula. Base formula. See, this base formula contains only the carbon and the hydrogen. Carbon and the hydrogen. So the base formula is given by M/13 equal to small n plus R/13. R/13. So then the base formula is given by Cn plus Hn plus R. Suppose the molecular weight is 94. So the molecular weight is 94. So it is excluded the heteroatoms. This is excluded the heteroatoms. Exclude the heteroatoms. So the 94 divided by 13, which is equal to, we can go for the LCM, okay, and find out 7/3/13. So here the n equal to 7 and R equal to 3. The base formula is C17H10. And this base formula is taken as such, and if any heteroatom is present, as already I have told from the this can be obtained from the mass spectrum, and also we can have idea from the analysis, the normal the qualitative analysis, what are the elements present. So you can include the elements, other elements that is present other than the carbon and the hydrogen, and that gives a molecular formula. That gives a molecular formula. Alright, follow my point. So first you find out the rule of 13 that tells about to find out the base formula, and add the heteroatoms that is present, that is found from the various techniques, by the qualitative analysis or from the mass spectrum. And the third one is that we must consider the isotopic abundance. Okay, so if chlorine is present, already I have told, you will get a M and M plus 2 peak of 3:1 ratio, and if bromine is present, and we will find in the mass spectrum the molecular ion peak, of ratio the 1:1. And we have many other ideas, the analysis of fragments obtained. That is, if it is you are getting the peak at m minus 15, that is because of a loss of methyl groups. And if you are getting the peak at m minus 18, that is because of the loss of the water molecule. And if you are having peak at m minus 33, that is because of the loss of both methyl and the water molecule. So these are the small information you can must have to find out the deriving the molecular formula from the molecular weight. And finally, we must also taking the consideration of the results that are obtained from the other spectroscopic technique like IR, NMR and UV visible, etc. Let us go for the mass spectrum of the discussion of the mass spectrum of some compounds, some representative compounds. The first one is ethyl benzene. Okay, so here the ethyl benzene, the C6H5 CS2 CS3, we have the aromatic system and a side the side fragments the ethyl molecule. Here the molecular peak is formed, which has the MZ value of 106. So here we are having the cationic molecular peak of MZ 106. Here normally the aromatic system, the benzylic cleavage is more popular. That is C6H5 CS2 cleavage is more popular. So here also this 106 the molecular peak that cleaved as the benzylic cation, removing the methyl radical, and the benzylic cation that undergoes the rearrangement forming tropylium cation, which are having M by Z equal to 91, which appears as a base peak, which is very stable. Okay, or you follow my point? So any benzylic molecular ion or the benzylic cation that will undergo rearrangement to form the tropylium ion. Okay, so this is the mass spectrum of ethyl benzene. And the second one is the mass spectrum of methoxyethane. The methoxyethane is a ether. It is unsymmetrical ether. One side we are having the methyl group, a smaller group. The other side we are having the ethyl group, a bigger group compared to the methyl group. The most for ethers, the most characteristic fragmentation mode of ether is the loss of one of the alkyl group along with the oxygen atom. So the oxygen atom with the alkyl group that goes off, we call it as oxonium ion, RO plus or the alkyl cation. Either can be formed, either oxonium, both can be formed, but the most popular or most intense peak is because of the formation of the oxonium ion rather than the alkyl cation. Okay, these types of ions formed is as a result of the alpha cleavage. Alpha cleavage means the bond that is attached to the oxygen atom. So that undergo cleavage preferentially, and that is lost. Here is the example for the fragmentation of the methoxymethane. So the methoxymethane, the molecular peak appears at the M by Z 60. And because of the removal of the hydrogen ion, it forms a peak at M by Z 59. And we have the other fragmentation also, the removal of the methyl radical, forming the oxonium ion, which contains the ethyl group which are having the MbZ 45, which appears as a base peak. As already told, for the ether, the oxonium ion appears as a base peak. And the other possibility is the molecular ion which are having MbZ 60 that remove that lost the OCS3 cation, OCS3 cation, and forming a peak of MbZ31, MbZ31. Okay. And the next one is a mass spectra of acetophenone, which is an example of the fragmentation process involved in the ketone. Here it is a aromatic ketone. Here it is a aromatic ketone. So generally the ketone undergoes the alpha cleavage, as already I have discussed in the ether. So the bigger group on either side of the ketone, okay, or a carbonyl group, which is lost preferably. Okay, so the mass spectra of acetophenone is characterized by the appearance of a molecular ion peak of MbZ at 120. So we are having the molecular peak of 120, and this 120 molecular peak undergoes the fragmentation by the loss of C triple bond O. That's a CO, okay, which form the MbZ fragmentation of 77, that is the benzene cation. Further it undergoes fragmentation, forming a molecular fragmentation peak of MbZ the 51. Okay, so that is a mass spectrum of acetophenone. The base peak is the 105 and the molecular ion peak is 120. And for the analysis of the amine, the aliphatic amine, let us see the mass spectrum of n-butylamine. Generally, here also the the bond, the carbon which attached to the nitrogen, okay, that goes off with the nitrogen. So the CN, okay, that undergo fragmentation. So here we are having the n-butylamine, the CS3, CS2, NS2. So the CS2, NS2 that will undergo fragmentation preferably. This is applicable for any amines, any aliphatic amines, and that will forms a base peak. That appears, the intensity of the peak is very, very high. Here here we have the molecular peak of MbZ 73, and it forms fragments of the high intense fragment, that is a base peak of MbZ 30, that follows the nitrogen rules also. That means the molecular is the odd number, that's MbZ 73, and it forms the fragments of even number. And the next one is the propanol, 1-propanol. So this shows the fragmentation that occurs in the primary alcohols. Normally the alcohols easily undergo fragmentation by losing hydroxyl radical, okay, the OH, that's M-17, or water molecules, the M-18 molecules. The presence of molecular ion is very, very small because of the primary alcohols or the secondary alcohol. Already we were discussed in the part 1. Their molecular ion is very small, and the tertiary alcohols that will not show any molecular ion. Okay. So commonly it loses an alkyl group attached to the OH, forming a oxonium ion. Here it forms a fragment of CS2OH plus, and that appears as a base peak in the spectrum. Okay, in the spectrum. Its value is MbZ 31. So for any aliphatic alcohol, the MbZ 31 is predominant. For the lower alcohols, lower aliphatic alcohols. Here we are having the molecular peak. It's very, very small, and a peak of M plus minus 18, and a base peak of we are having MBS at 31. And for the mass spectrum of 1 pentanol, mass spectrum of 1 pentanol, here this is a long chain alcohol. Here this OH have the gamma hydrogen. OH have the gamma hydrogen, and this type of alcohol which contains gamma hydrogen undergoes the McLafferty type rearrangement. McLafferty type rearrangement. Okay, and that rearrangement product which appears as a base peak. And we are having a molecular peak of the trace amount of molecular peak at M is at 88, and a comparative intense peak at of M minus H2 at M is at 70, and because of the McLafferty rearrangement, that fragment M is at 42 appears as a base peak, appears as the base peak. So I cannot discuss the fragmentation pattern of all the compounds. I have given the representative example. You take the representative example and apply whatever the example given in the competitive exams or your semester exams. Okay, and before ending into the our discussion, we can discuss on the McLafferty rearrangement. Okay, the McLafferty rearrangement is very common to the molecule contains gamma hydrogen atom with respect to the carbonyl groups. Carbonyl groups. So what are the requirements? The molecule must possess a heteroatom, a 5 system, that is a double bond. It may be a carbon double bond oxygen double bond and a gamma hydrogen. And here we are having a carbonyl group having the gamma hydrogen. So the molecules are so arranged or depicted here so that a cyclic system or cyclic 6-membered cyclic transition state is formed. So always in the organic chemistry, if the molecule undergoes rearrangement through the 6-membered transition state, it is very stable. It is occurs preferably. And here the abstraction of hydrogen takes place by the oxygen. The abstraction of gamma hydrogen takes by the oxygen atom takes place simultaneously. The alpha beta bond breaks up. Alpha beta bond breaks up. So it is a simultaneous rearrangement. Simultaneous rearrangement, and it forms the oxonium, that's the hydroxyl cation. Hydroxyl cation rearrangement product which appears as a base peak, appears as a peak along with the alkene which is a neutral molecule. So this McLafferty rearrangement is common to the carbonyl groups which contains gamma hydrogen. And the final one is the retro-Diels-Alder reaction. So you know the Diels-Alder reaction is 4 plus 2 cycloaddition, the addition between the diene and the dienophile. And this retro-Diels-Alder reaction is already we know that the mass spectrometry is arises because of the fragmentation of the molecules. Here in the retro-Diels-Alder reaction, it is a reverse of a Diels-Alder reaction. The molecule the rupture of the alpha bond leading to a cationic dione and the neutral alkene. So the types of the it may be a pair of electron mechanism or a radical mechanism. There are two types of mechanism involved in the retro-Diels-Alder reaction. A simple reverse of Diels-Alder reaction, it's a retro-Diels-Alder reaction. Thank you very much for listening my lecture. I will be very happy if you subscribe my channel and like my videos and share my videos in my channel. You can see similar number of videos on various topics on chemistry. I hope you like this video. Thank you very much.